Check. Good morning, everyone. I'm Ahmad Douglas, and I am Head of Information Security and Risk Management for Xfinity Home. I'll be your host and moderator for this session. So our topic for the better part of this morning is how I learned to stop worrying and love the Internet of Things. So I think there's a ton of publicity on this. We can't go one day without seeing another article about IoT security and what it portends for the world. I think in some ways it really is more of a classical security problem than we give it credit for. That, you know, the things that we're not getting right as an industry are straightforward. Things like, you know, building decent access management, using decent passwords, embedding the right certificates, patching things in a scalable way. So I think there's a lot of things that we have challenges within our enterprise networks that we can learn lessons from and do well on our existing devices. That said, there are some really interesting things in the Internet of Things that make it more complex. Of course, the scale, which we always find a new stat on when we log into our LinkedIn of how many connected devices there will be, but also just where these devices are placed, that many times they have some sort of a restricted or abbreviated user interface, so it's harder to get to it to do the maintenance that's necessary. And then also, you know, as many of us are discovering with this recent WPA2 issue, that one of the things about IoT that's so interesting is how it ages and how, you know, these devices are designed to exist for so much longer than maybe an IT refresh cycle is in our homes or in our businesses. And so how do we maintain those vendor relationships and the other aspects needed to patch these things for not a few years, but potentially a decade or more. So with that, I'm very excited to introduce Mr. Kirill Levchenko. He is an associate research scientist, Dr. Levchenko, I apologize. Associate research scientist at UC San Diego. He received his PhD from UC San Diego in 2008. And his research includes network routing, network security, e-crime and online service abuse, SPAN embedded system security. And he's going to tell us today about an analysis of emission defeat devices in modern automobiles. So welcome, Dr. Levchenko.
Thank you. Thank you. So today I want to tell you about some work that we did at the University of California, San Diego, together with my colleagues there, as well as collaborators from the Ruhr University Bochum in Germany, and independent researcher Felix Domke. So I think most of you have probably heard about the Dieselgate scandal in the news. The scandal concerns Volkswagen 2 and 3 liter vehicles, cars, that were found to emit 40 times the allowed nitrogen oxides in road tests. However, those same cars appeared to be in compliance during regulatory certification tests. In other words, in one mode, they behaved within limit, and the other, they exceeded the limit by 40 times. Volkswagen admitted to using a software defeat device when pressed by the EPA to alter vehicle behavior during standard emissions testing, so that during the test, it was within limits. In normal road driving, it exceeded those limits. Now, this turned out to be very costly for Volkswagen, costing it $24 billion as of last count, including fines and settlements. So what I'll tell you about today is how they did it, how this defeat device worked. I'll start with an overview of diesel emission standards and diesel electronic engine control. Then I'll walk you through the Volkswagen defeat device, which was used to do this and which cost Volkswagen $24 billion. And I'll conclude with some thoughts about the future of compliance verification. So diesel engines, unlike gasoline engines, which you're probably more familiar with, differ from gasoline engines in that the combustion is initiated by compression rather than by a spark. This has several implications, including that the diesel engines produce more soot, also called particulate matter, and they produce more nitrogen oxides, which is nitrogen oxide and nitrogen dioxide. And these are the two pollutants that diesel engine manufacturers have to worry about the most. Now, diesel emission standards have been becoming tighter and tighter over the last 2 decades. So here in this graph, you can see on the x-axis are the limits for nitrogen oxides per unit of energy, and on the y-axis, the limit on particulate matter. And it's gone down by about an order of magnitude in the last 10 years. This makes it very challenging to sell diesel engines in markets that have these strong limits. Now, one thing I should mention is how diesel engines are tested, or how vehicles are tested for compliance. Vehicles are tested on a stationary chassis dynamometer driving a fixed, publicly known test cycle. And the reason we do this is for fairness and repeatability, so that manufacturers can test vehicles on their own, and so that they can be assured that the tests are not biased against them. So this is what a test setup would look like. A vehicle is placed on these rollers, and there's a driver inside who will drive a fixed cycle of certain speeds at certain times. In addition, not shown in this picture, there would be a device hooked up to the tailpipe, which would capture all of the pollutants and then measure them in a laboratory. This is the FTP75 test cycle, which is used in the US. The x-axis is time, and the y-axis is vehicle speed. So a driver who would be driving this test cycle on a chassis dynamometer would have to follow this profile. So this is how we test vehicles. Now, what are the options available to diesel manufacturers to reduce emissions? Well, there are several. Inside the engine, you can alter fuel injection timing, which has an effect on the amount of pollutants produced. There's a technique called exhaust gas recirculation, where you recirculate some of the exhaust gas back into the combustion chamber, which can reduce nitrogen oxides, but it does have an impact on power. There are also several exhaust gas after-treatment options. These are things you do to the exhaust gas after it leaves the engine. So so the first is the nitrogen oxide storage catalyst, NSC, also called the lean nitrogen oxide trap. This is a mechanism which traps some of the nitrogen oxides, but does require some complex regeneration. There's also something called selective catalyst reduction, diesel particulate filters. For the first two there are for dealing with nitrogen oxides, diesel particulate filter obviously for particulates. The thing that makes these interesting is all of these require complex computer control. In other words, these are not just passive elements, but something that a computer has to control and regenerate. All of this control happens inside the engine control unit, which is basically an embedded system that reads certain inputs from the engine, including things like mass airflow, accelerator, pedal position, fuel delivery, and so on, computes a certain function, then produces outputs which actuate the fuel injectors, as well as control some other elements like valves that determine how much exhaust gas is recirculated. This is what an engine control unit looks like. This will be inside your car today. It contains a CPU, flash, EEPROM, ADCs, and some line drivers. In other words, it's a typical embedded system which contains a few specialized automotive components for controlling car-specific systems. Now, one thing I should point out is that the car maker is not the same as the ECU maker. The ECU maker is usually a different company. In the case of the Dieselgate scandal, there was one ECU maker, which was Bosch, which made all of the engine control units. The ECU code is usually customized or tailored to each customer or automaker. So Bosch's customers are automakers, and they might have certain requirements or certain behaviors they might want. Bosch would modify their code base in order to meet these particular requirements. In addition, each ECU is tailored to a specific vehicle model by adjusting calibration constants. These are constants that are baked into the firmware that alter how the ECU works. For a software analogy, you can think of these as modifying the constants in your executable file which would change how the overall system behaves. Calibration does not require access to source code. It's performed purely in the binary. Again, you can think of it as just tinkering with the constants in your read-only data segment of your ELF file. This calibration step is performed by the automaker or subcontractor, although some constants may be calibrated or set by the ECU maker. Once these are set, the ECU or the automaker tells the ECU maker, here are the constants we want, and the ECU maker produces a batch of ECUs that they can use in their vehicles. Here's a typical map. This is, you can think of it as a two-dimensional array constant, which defines the exhaust gas recirculation rate. In other words, how much exhaust gas is recirculated as a function of engine RPM and the amount of fuel injected. So fuel injected is on the y-axis in cubic millimeters, and RPMs is on the x-axis. So here you can see you're calculating the, how much exhaust gas is recirculated, ranging from 46 in the upper left to 0 in the other end. So most engine behavior, in other words, is going to be defined by maps like this. There'll be a generic algorithm which will implement some kind of a general engine behavior, like injection timing and so on. And the specific values and amounts and points at which this happens will be determined by the automaker using these constants. Okay, so now we have all the background you need to talk about the Volkswagen defeat device. This defeat device originated with Audi in 2004. This is according to the New York Attorney General's complaint that they filed. I'm showing you an excerpt from their complaint where they say that Audi developed and deployed the cycle-beating defeat device software on its European market Audi 3-liter V6 diesels from 2004 to 2008. Because of its noise-reducing properties, Audi dubbed this defeat device the acoustic function. So acoustic function, as you'll see, will become this euphemism used throughout the documentation to refer to this defeat device. While this was identified, obviously, engineers at Audi knew about this. And Audi is a subsidiary of Volkswagen, I should mention. The specific code in the firmware was first identified by our collaborator Felix Domkin, was revealed by him at the CCC 2016 conference. Okay, so this acoustic function, what does it do? Well, ultimately, this acoustic function, which I'll walk you through in a second, calculates a single flag called, in this case, ST-NS-char core. It's 0 in normal driving and 1 if the vehicle is undergoing emissions testing. So this acoustic function, its purpose is to determine whether the vehicle is currently undergoing an emissions test. And if it is, it'll set this value to 1, and that will alter the behavior of certain systems inside the vehicle in order to be compliant. Specifically, it'll alter the exhaust gas recirculation rate, which, as I mentioned, reduces nitrogen oxides but has some implications on vehicle performance. Also alter the behavior of DPF regeneration and other after-treatment mechanisms, as well as fuel injection. So everything I'm about to show you actually comes from documentation produced by Bosch for Volkswagen. So as I mentioned, Volkswagen is the one that calibrates the engine control unit for a specific model. The documentation that they need in order to do this is produced by Bosch in what's called a function sheet, or in German, Funktionsrahmen. These functions are described using data flow diagrams, which you will see. And because these are valuable to people who want to tune their car, some of these function sheets have been leaked to the tuner community, to the online community of people who like to modify their car firmware. So this is where we got these. These are publicly available documents that we found on the internet, again, circulating in forums and on sites that cater to the car tuners. Okay, so again, we're looking now in the Bosch documentation available publicly if you know where to look. And this is the acoustic condition, this famous function that calculates whether you're undergoing a test or not. This is the function that cost them $24 billion. Now, as you can see, the goal of this function is to calculate a Boolean value. And again, it'll be 0 under normal driving and 1 if the vehicle is undergoing test. And therefore, the behavior should be modified to be in compliance. So, the first element of this is that there's a flip-flop. All of you, I'm sure, are familiar with what these do. It'll remember the current value calculated by the block that was provided at the S input. And if the R input is ever 1, it will reset that value to 0. This is an AND gate. And all 5 conditions must be true to set the flip-flop. In other words, for us to decide that we are undergoing an emissions test, the first thing that needs to happen is we have to satisfy all of these 5 conditions. Now, I won't walk you through all of them, but maybe we can start with just one. At the top, you have the, this is the coolant temperature threshold. You can see 2 values with the _C suffix. These are constants that would be provided by the manufacturer, although this code itself is produced by Bosch. So again, Bosch produces this code, manufacturers tune it for their specific vehicle. So the first condition is that the coolant temperature, the engine coolant temperature, has to be between this specific range. Now you'll recall that the vehicles are tested in very precisely controlled and publicly known conditions. So the auto manufacturer knows exactly what the coolant temperature is supposed to be during a test, and they can set this to specifically identify a test condition. Now the other conditions are fuel temperature, oil temperature, things like that, and environmental pressure. If these are all within limits that the manufacturer expects to be during a test, then it will set the flip-flop, and initially the acoustic condition will be satisfied, or this acoustic function flag will be 1, meaning it is undergoing a test. Now, the other important element is what happens to change that output. And to change that output, the reset input comes from the second flip-flop here. You can see this flip-flop does not have a reset input, which means that once set, it will not reset until the next power cycle. This means that if any of the conditions to reset this flip-flop are satisfied, they will stay satisfied for the rest of the driving cycle, and the vehicle will no longer consider itself to be under test. This odd-looking gate is actually an OR gate. It simply says that the output is 1 if the sum of the inputs is greater than 1, effectively an OR. There are 4 conditions that may be satisfied in order to reset this. I won't go through all of them. You can see there's a timer in there so that the acoustic condition can be deactivated after a certain amount of time. The typical driving cycle tests are about 25 minutes, so this is a kind of fail-safe mechanism where you can turn that off. The most interesting element, however, is the last condition. So the last condition is determined by this AND gate. All 7 conditions must be true in order to set the deactivation flip-flop, the second flip-flop that I showed you, thus turning off the acoustic condition. In other words, when all 7 of these are true, we will determine that the vehicle is not undergoing a test. You can see that all of these elements are actually the same, so I'm going to zoom in into one of these elements. You can see, again, it has a flip-flop where it remembers the output. It's never reset, so once the particular condition is met, it will not be cleared. The condition calculates, the input there is a map, and it calculates a function of 2 variables, time and distance from the start of the driving cycle. It compares these to 2 bounds. And here again, q equals 1 means that we've shot through both the upper and lower bound, or sorry, we've shot through one of the 2 bounds, or potentially both, that are determined by these curves. So this is, again, a curve that is a function of time. You compare the value of those curves against the distance traveled, and if you shot through one of them, that means that this flip-flop will be set, and you are no longer satisfying this condition. When all 7 will be set, then you're not in a driving cycle. Okay, great. So what are these curves? It's a little bit opaque what's going on. However, if you plot these curves, and these are curves pulled out of the actual firmware, the firmware part number is listed over there. If you plot these curves, you have 2 curves, the upper curve and the bottom curve, and they create this interesting little channel in between. It just so happens that that channel exactly matches the FTP 75 test, the federal test used to certify vehicles. This means that if the vehicle, the time distance profile, falls between the 2 upper and lower bounds, you will determine that you are undergoing a test. However, if at any point your time distance profile exceeds one or the other, either you should go faster than supposed to or slower than supposed to, then you'll decide you are not going through an FTP 75 test cycle. And therefore, that condition will be deactivated. Here's another profile which matches the European test cycle. The effect of these is this. Exceeding either the upper or lower bound will set the flip-flop. There are 7 of these, and it's the one I showed you. The ECU will remember that the curve did not match the driving profile. And once all 7 curves are ruled out, the acoustic condition is turned off. In other words, if the car realizes that none of the 7 known driving testing profiles match, then the car is not undergoing a test and it can revert to normal behavior. This is what allowed, and this is perhaps the most sophisticated element of the Volkswagen defeat device, because those profiles match exactly the curve I showed you earlier for a known test. So once the car sees that the speed you're driving and any particular time you're driving at does not match a known test, it can rule it out. And once it's ruled out all 7 tests, it realizes the car is not tested, and it reverts to its normal or polluting behavior. Now, the one I showed you had 7, actually the number of curves increased with time. And later curves starting in 2014 included an additional steering wheel check. As you recall from the picture, the vehicle is placed on a dynamometer where the wheels are facing straight forward. The steering wheel check the steering wheel to fly more than 20 degrees in either direction, and you know you're not on a chassis dynamometer, and you know you're not being tested. So this additional provided an additional constraint that you had to meet in order for the vehicle to think it's undergoing a test and follow the compliant behavior. So once we've calculated this flag, we're going to use it, or the firmware is going to use it throughout the rest of its operation, throughout the rest of its modules, to modify what it does. Typically, and I won't go into details, but typically this flag switches between 2 parallel computation paths with different calibration constants. So depending on whether the acoustic condition is 0 or 1, vehicle behavior will follow either one calculation path or another. Additional calibration values are then used to determine how each of these logic paths behave. We did an analysis of this, and we looked at all of the documentation we could find, all of the PDFs we could find online to see what systems were affected by this flag. As time went on, more and more systems were affected. You can see in this table, it's also in our paper, which was presented at Oakland, I believe, this year. You can see the number of systems as time is increasing going down the list. As time goes on, more and more parts of the vehicle, or the parts responsible for things like injection timing, EGR recirculation, and so on, increases. In addition, the number of curves tested, in other words, the number of possible emission test cycles that the vehicle was comparing against, increased from 5 to 7 to 10 with the addition of the steering wheel check. Okay, so now you know how the Volkswagen defeat device worked. You know how they cheated emissions tests. The natural question is, how could this happen? This defeat device was in use since at least 2009. However, it took independent testing by West Virginia University to find this. The simple answer is that black box testing, as we do for vehicles today, with a fixed cycle makes it very easy for manufacturers to cheat. And the reason it's easy is because the vehicle has complex software control. There's an embedded system controlling this that has access to many parameters, some as simple as a timer, as well as environmental conditions, which it can use to determine if it's being tested or not. You can think of this as being very similar to anti-VM detection or red pills inside malware that's used to determine if it's being run in a controlled environment by an analyst or not. So, as software people, which is I think what we're most of us are, it's natural to ask, well, what can we do about this? Is there a software solution to this? Specifically, can we detect defeat devices automatically? The answer is yes, if we know what they are. In the case of the Volkswagen defeat device, we knew exactly what they were doing. We knew what to look for, and we could build a software mechanism to find all instances of their defeat device throughout many firmware images, which is what we did for the paper. However, we cannot do this in the general case, or I argue at least that in general it's very difficult to detect a defeat device because it can be implemented in very subtle ways. It is too easy to hide an indirect dependence, and you still need to understand what the code actually means, what variables it's testing, and so on. So I don't think that there is a software solution to this problem, or at least a pure software verification or detection mechanism that we can do. That leads us to the challenge that regulators are going to have to deal with in the next 5-10 years as more and more of cyber-physical systems come under computer control, and at the same time we have regulations imposed on them, such as with vehicles, energy-efficient appliances, things like that. So one question is whether we can do fully formal software verification. These are the kinds of things you might want for medical devices, aircraft systems, nuclear power plants. Unfortunately, this poses a huge manufacturer burden who would naturally be the ones who would have to be doing this. And you need some assurance that the formalization of the properties you're proving is correct. You could imagine a manufacturer saying that, well, actually, this variable means speed, and this variable means total pollution emission, whereas in fact it means something else. In addition, cyber-physical system verification, where you're verifying a physical property based on software behavior, is still in its infancy. We just don't have that technology yet. The approach we're pursuing right now is to design a monitor that will observe system behavior at runtime to ensure compliance. We can then formally verify a monitor, which is just a small part of the overall system, to ensure that it's behaving correctly. Another alternative we're examining is whether we can verify correctness of monitor computation rather than monitor software itself at runtime in order to observe or ensure that the full system is behaving correctly. I'm out of time, so I'll conclude. I've shown you the Volkswagen defeat device. There was an acoustic function which precisely detected test conditions. The outcome of this acoustic function is used to alter behavior of multiple systems that were relevant to vehicle emissions. Because the vehicle is controlled by a software system, it was very easy to detect and defeat regulatory testing. This leads to an important challenge that we as the software and security community will have to address or help regulators address, which is how to ensure regulatory compliance of software. There are new technical challenges as well as the potential for new regulatory regimes. I'll stop here. Thank you. I'll take questions.
Thank you. Thank you, Dr. Levchenko. So given that we're just a little bit behind schedule, I'd ask, we'll take the questions to the side. And I would welcome Robert Albach on